Welcome to Topcast and to my third episode, analysing some writing on the topic of objectivism. In the first episode, I analysed Ayn Rand in her own words, directly, from her work Introduction to Objectivist Epistemology. And in the second, I began to analyse an objectivist scholar who has read and written widely on objectivism, and in terms of epistemology has attempted to clarify and perhaps take further some of Rand's own work. Now, I've produced podcasts and written articles before about all manner of things, from Bayesian epistemology, socialism, environmentalism, even religion, some of the controversial topics of our time. But few topics generate the style of response I get when I speak about the epistemology of objectivism. Now, from afar, I've already noticed this when it comes to economics. People do wear their economic theories somewhat religiously, and this can be unfortunate. What I mean by this is that people think they know their own side, but they don't take much time to understand the counterclaims being made and why they are being made. As John Stuart Mill said, quote, "He who knows only his own side of the case knows little of that. His reasons may be good and no one may have been able to refute them. But if he is equally unable to refute the reasons on the opposite side, if he does not so much as know what they are, he has no ground for preferring either option, nor is it enough that he should hear the opinions of adversaries from his own teachers, presented as they state them and accompanied by what they offer as refutations. He must be able to hear them from persons who actually believe them. He must know them in their most plausible and persuasive form." End quote. So yes, that famous way in which he began. He who knows only his own side of the case knows little of that. This is what I'm trying to do. I'm trying to follow what Mill implores us there to do. I'm not merely listening to the people on my side of the case when it comes to objectivist epistemology. I'm going to Ayn Rand. I'm going to her supporters. I'm quoting her at length, I think. Her supporters at length, I think. And I'm going to bring in yet a third person today who actually wrote a book about the use of induction, supposedly, in physics, who is also an objectivist, an avowed objectivist. Now, aside from my episodes on objectivist epistemology, perhaps there is one other topic that has generated a similar visceral response in people. That's when I speak plainly about the need for infinite progress and its implications. In other words, claims like, we need more people, and that in the main, more people are almost entirely upside. And the reason being, people are the sole originators of explanatory knowledge, which is to say, solutions and hence progress. They, people, are not sources of problems, they're sources of solutions. And the solutions are the sources of better problems, whose solutions will be found by people. And people are, first and foremost, producers and creators, not consumers and destroyers. And so that whole perspective that I've just said there, that I've just outlined, that really upsets people. And so I get a lot of response when I say things like that. But one needs to take time to understand the environmentalist's perspective on these things and the Malthusian impulse and the arguments that Malthus and his descendants, his intellectual descendants, have made. And then you need to have explanations why those arguments are wrong. You need to understand them in the first place. Although in the case of environmentalism, it is relatively easy to come by all those arguments. After all, we're saturated in them in the media and everywhere else. Every newspaper you pick up has some explanation each day about the evils of people and the environmentalist movement and the importance of it. It is the culture in which we swim. It's the zeitgeist. And if you just went to school after about 1970, perhaps even a bit before, you were indoctrinated with all that stuff. So people who managed to get out of it, heroes of a kind. Everyone is now an expert in environmentalism, more or less, once they've graduated high school, because they've experienced a 12-year course of it. All the way from the first year of infant school through to the day they graduate high school. They are saturated with lessons on environmentalism, the evils of people, how the world is going to hell in a handbasket, all that sort of stuff. That's environmentalism. Epistemology, on the other hand, is totally different. We do manage to build a folk epistemology, and often our common sense use of words like know, K-N-O-W, tracks how it entails fallibility and the containing of errors. My go-to example is, of course, that the high school student who studied some basic physics will know Newton's law of gravity. It forms part of their knowledge once they've learned it. Even when they later learn it is strictly false, they still know it. It still counts as knowledge. And they can still say, I know it. And also, I know it to be false. It is only in academic philosophizing the linguistic gymnastics begin to deny this common sense meaning of knowledge and what it is to know something. They say knowledge must be some kind of justified, true belief. Of course, Newton's law of gravity, known false, cannot be true, so should not be believed, and thus no one is justified in saying they believe it if they know it's false. And it cannot be justified by any process anyway. So common sense tracks what Popper explained about knowledge, but not what the other intellectuals explain about how knowledge works. They get it all wrong. They overthink it. So I've spent time reading Popper's critics, and I've read Ayn Rand, and I've quoted Ayn Rand and one of her supporters so far, bring in a third today. But people say I'm still misinterpreting her. I have not, thus far, had anyone quote myself back to me. No one has refuted anything in Popperian epistemology so far, using some specific quotes or examples. No one has explained a flaw in my examples of how we know about what stellar nucleofusion is or what dinosaurs are, though we observe none of those so-called facts of reality. And yet I'm reading comments and tweets of the kind re-explaining Rand in their own words, which leads to a further proliferation of interpretation of Rand, which somehow makes my point for me, that even with things like what someone wrote in black and white is still interpretation all the way down. But anyways, at least one tweeter remarked, I am grossly misunderstanding the written word and spreading misinformation. So that's fun. I'm also reading in multiple DMs, I did not read enough or quote enough from Rand, and I spent too much time explaining Popper. I should have been explaining more about Rand, which is kind of a damned if you do and a damned if you don't kind of critique. Some listeners, I guess, would have preferred simply me reading the entirety of an objectivist paper or book without commentary, or maybe just with some approving sounds. So anyways, my point here is that there is something special in this respect about objectivism. My diagnosis is, and this will upset the objectivists, is that epistemology, having the particular form that it does, turns it into a system of belief to be defended. One interlocutor on social media basically agreed and said, yes, it is, and this is a virtue of it, and we should defend the truth. Which begs the question, of course. My real concern is no one quotes Popper. No one quotes him. Back to me. The favour is simply never returned. There is a talk on YouTube, for example, by Don Watkins and Jason Rhimes, objectivists. I've watched where those objectivists critique Popper, but I've never bothered to do much more than watch it because they are focused narrowly on falsification and essentially reduce Popper's epistemology, like almost all his critics ever have, to that one concept, and they barely quote him at all. There's nothing about objective knowledge, problems and solutions, conjectures and refutations and so on. So my whole problem there in, trying to respond at length to something like those guys would be, well, I'd be charged with the crime of simply explaining too much Popper again in my critique of the objectivist perspective. But that's the thing about conjectural knowledge in Popper's sense. Knowledge is critical. It's critical, which means that once you have some knowledge, you have an explanation. It's a criticism of all the other alternatives out there. So in explaining Popper's epistemology, what I am doing is critiquing every other epistemology, including Ayn Rand's objectivism. That's the whole point. The whole point under Popper's epistemology is that something like general relativity serves as a critique of all other theories of gravity, including Newton's. And they all come up short, shown false by experiment, but refuted by the existence of the explanation, the scientific explanation of gravity. So too with neo-Darwinism. It is a critique of every other theory of how speciation occurs and the variety of life on Earth. Name your theory. Regarding it as a critical piece of knowledge means it is a criticism. It exists as a criticism of all the other knowledge we have out there. It's a conjecture and it's a criticism, all in one. That's what knowledge is. And in the case of where we say this is the explanation of something, It's a successful criticism. It's a successful criticism of the alternatives. Okay, Newton can be a criticism of other theory. Well, Newtonian gravity can be a criticism of other theories of gravity under Popperian epistemology. It's just that it fails in doing so. It can't achieve a successful criticism of Einstein. It fails in being able to do that. It's not a valid criticism. Why? Because it fails to account for a whole wide variety of phenomena. The bending of starlight during solar eclipses, the precession of Mercury's orbit, gravitational waves, the behaviour of black holes and neutron stars, and technically speaking, the orbits of all other planets and the GPS system and so on and so forth. So, whatever the case. Today, I'm up to part 2 of my discussion of Thomas Miovas' paper on induction. I'm going to get there. David Deutsch asked me after the first episode I did on this, a simple question when it comes to objectivism. I'll just paraphrase the question he asked me. The question was, under objectivism, is the force of gravity a concept? Well, that's a great question. That's brilliant. Now, of course, what I'd say is this is one of the problems with the abstract nature of the way Rand and other objectivists write about epistemology. We don't get down to brass tacks, so to speak. Although today I will be providing some commentary on one objectivist who tries to talk about examples from history, the history of physics. So that's good. Gets it all wrong, of course, spoiler alert, but at least we have something, some meat on the bones we can talk about. We don't get that from Rand, we're not getting that from Thomas and almost anyone else. But on this question, on this question of, is the force of gravity a concept under Ayn Rand's objectivism? Is the force of gravity a concept? Let's say they do think it's a concept. Let's say the answer is yes, the force of gravity is a concept according to Rand. Well then, what we have is a concept that is entirely fictitious because there is no force of gravity. We know that now. Einstein's general relativity explains what gravity is, and it's the curvature of space-time. It's not a force. So then, concepts, knowledge, can be false under objectivism. But how does that happen? If concepts are just induced from the facts of reality, and the facts of reality cannot contain falsehood, how did we get falsehood from truth? Is it because reason is fallible? In which case, we have conjectural knowledge. We have Popperian epistemology, just with the unnecessary philosophical baggage of, by the way, we also observe the facts of reality, but they serve no actual purpose in being called as such or being starting points because where we end up is false knowledge anyways. Okay, so maybe they say, no, the force of gravity does not count as a concept because it's known to be false. Well, okay, but presumably in the 18th and 19th century, it did count as knowledge because it stood in relation to people then as any unrefuted explanation today or content of an unrefuted explanation today stands in relation to people right now. So somehow the force of gravity transitioned from being a true concept to a false concept. So again, we have a conjecture and a false one, a refutation showing it false. Again, no function for the observed facts of reality. Newton merely conjectured an explanation of gravity. It's important to keep in mind, Newton postulated a physical force. He wasn't merely making predictions, he was making a substantial claim about what reality consists of. He didn't know what the cause of the force was. He says there was this attractive thing. How exactly it worked, he didn't know, but okay. He still said it existed, though. Yeah, it existed, and Newtonians after him and physicists say, well, according to this theory, it implies a force. It didn't imply the curvature of space-time. Okay, these are different physical things. There's the sense in which one strictly contradicts the other. It's not merely about contradictory predictions, although that's part of it. That's how you go about measuring the differences between these things, and ultimately the falsification happens. But they're postulating the existence of things in reality. Either the force is there in reality or it's not. Either the curvature of space is there, this space-time thing is really there and can warp and bend, or not. Okay, it's just like saying giraffes exist or not. The force of gravity exists or not. Okay, you can't have it both ways. It's not like Newton's a little bit true on that point. It's not true. He's not right. Anyway, in either case, whether the force of gravity exists as a concept or it doesn't, there must exist misconceptions, right? Which is Popperian to the core. Nothing was being induced, or insofar as it is induced, then this use of this word induced or induction is simply conjecturing an explanation. And it is a fallible process, error-prone, And the lesson of Newton is the lesson for all knowledge everywhere, all the time. It could be false. It's always conjectural, and it cannot possibly be induced from the observed facts of reality. Because if it was, then we'd have certain knowledge. We'd have the facts of reality, the truth. We don't. Because reality can always contradict your so-called facts of reality. So how could they have been facts in the first place? Unless, as I explained in the last episode, the facts come at the end of the process. Once you have this explanation, this conjectured explanation, then from those you can derive certain facts. You can derive certain facts. So you have the big theory of particle physics, and from that you derive certain facts. Like, electrons have a particular mass. That's a fact. Or a particular spin, or a charge. Electrons have a negative charge. That's a fact that comes at the end of the process of figuring out what these things are. The big grand explanation. You don't start with electrons are negative. You don't even know they exist yet. You don't know what they are. Okay, you detect negative charge, but you don't know they're electrons. You don't know they're particles. They were originally cathode rays. Anyway, one could just replace the force of gravity with something like species or group selection in evolution. Is group selection in evolution a concept under objectivism? I mean, even today, people will claim that what is happening in Darwinian evolution by natural selection is that individuals within a species are being selected for or against, or even group selection is a thing. But now we know what the unit of selection is, the sole unit of selection. It's the gene. You do hear some people, intellectuals, prominent podcasters, scientifically minded, mind you, wanting seemingly to be some kind of political centrist on this point by explaining evolution as some mix of gene or individual or species or group selection, as if the debate is still going on. Well, what can you do? Now, before I begin the readings, as I say, from Thomas, the other matter on my agenda today is that I was implored to read a particular book. People just said, well, you've got to read this book. You've got to read this objectivist tome that will answer all your questions. And the title of it is, quote, The Logical Leap, Induction in Physics, end quote, by an objectivist called David Harriman, and with a foreword by Leonard Peikoff, one of the great luminaries of objectivism. So I got the book, and I read sections, and I'm sorry to say, nothing new. It did not persuade me. I went straight to the parts I was really interested in. How did universal gravitation come about, and how do we marry up the existence of Newton's theory with Einstein's theory? What does he say about that? Because whatever is said about that tells me the whole story about what this fellow thinks about how knowledge is constructed. So we're going to go through that section. But before that, well, let's go to what he said about Popper. Okay, word search on Popper. Of course, he comes up. Oh, it's a complete hatchet job, of course, as you would expect. He doesn't get quoted. His name appears twice in the text. Here it is. I'll read the passage in full. This is the complete treatment by Mr. David Harriman in his book all about the use of induction in physics. This is what he says about Popper, the sum total. Quote, During the past century, however, many philosophers have rejected the validity of induction and argued that every generalization is an error. For example, Karl Popper claimed that all the laws of Kepler, Galileo and Newton have been falsified. By demanding that a true generalization must apply with unlimited precision to an unlimited domain, Popper upheld a mystical view of truth that is forever outside the reach of man and accessible only to an omniscient God. In the end, he was left with two types of generalizations, those that have been proven false and those that will be proven false. He was then accused by later philosophers of being too optimistic. They insisted that nothing can be proven, not even a generalization's falsehood. End quote. That's it. The entire book, which is 300 and something pages, that's what you get about Popper. Not one quote from his work, nothing. Just assertions about what he thought. That's the standard of scholarship we've got here. Popper did not claim all the laws of Newton have been falsified, as claimed there, and he did not say everything will be proven false. That's not the epistemology. The fact that knowledge contains error, yes, sure, does not mean we will find it and therefore prove it false. And anyway, this word proven's the wrong word. And then the author wants to link Popper to relativists or skeptics. It's just completely ignorant. It's not fair. In the same way that I keep saying the favour is not returned. The objectivists are not connecting with quotes. Pull out some quotes and take exception to them. Fine. Let's explain Popper in his own words. Summary probably of a summary. In fact, well, he does link to a reference to objective knowledge, but it's just a book. There's no page number. But let's go on to the meat of the matter, so to speak. This book then goes on to explain how Newton discovered universal gravitation. The book provides a history of what Newton used universal gravitation to do in predicting tides and shapes of orbits. And he just asserts that the move from Kepler's laws to an inverse square law is induction. And further, in a chapter called Discovery is Proof, the claim is that the mathematical proof of the inverse square law of gravitation amounts to its discovery. At no point do we concern ourselves with the fact that it is strictly false, refuted by experiment. The author writes on this, quote, "A rigorous process of inductive logic enabled Newton to climb from narrower generalizations to his fundamental laws," end quote. We're never told what this inductive logic is exactly. The description offered is perfectly consistent with Newton conjecturing the explanation. He goes on to say, quote, the author says, quote, "For example, he did not leap to the law of universal gravitation and then search for confirming instances. Rather, as we saw, he began by identifying the nature of the solar force on the planets. In the Principia, he then showed that a similar force is exerted by Jupiter and Saturn on their respective moons, and he therefore had a law pertaining to both planets and moons. He next showed that a similar force is exerted by Earth on both terrestrial bodies and our moon, and he therefore had a law that applied to all bodies on Earth's surface, as well as planets and moons. He then showed that the attractive force is not merely exerted by Earth as a whole, but it is exerted independently by every bit of matter making up the Earth. His analysis of Earth's shape and precession and the ocean tides provided important evidence for this conclusion," end quote. Okay, so he showed, proved, or induced a complete falsehood, because there is no such a force. And he came up with the law not by looking at the instances where it worked in these different places and then generalizing to the law. No, he had the general law and then realized that necessarily it applied everywhere throughout the entire universe. So, of course, to each of those places, each of those instances where it applied. Anyway, the author goes on to say, quote, "If at the end Newton had been asked, 'Now that you have this theory, how are you going to prove it?' he could answer simply by pointing to the discovery process itself. The step-by-step logical sequence by which he arrived at his theory is the proof. Each step was the grasp of a causal connection by the mathematical processing of observational data. Since there were no arbitrary leaps, there is no problem of justifying them," end quote. So, according to the author, therefore, Newton's theory of gravity is proved and justified, and yet it's false, which is interesting. I wonder how the author goes about squaring this circle. They've got to mention Einstein eventually, right? And they do. So let's read what is said. Here we go. Strap yourself in. Quote, "The major axis of Mercury's orbit is observed to rotate very slowly. As seen from Earth, the total rotation appears to be about 1.56 degrees per century. Calculations show that almost 90% of this apparent rotation is caused by the precession of the Earth's spin axis, which is entirely explained by Newton's theory. Of the remaining effect, more than 90% is caused by the gravitational pull of the other planets, which is also explained by Newton's theory. That leaves less than 1% of the total observed effect, which amounts to 43 arc seconds per century, unexplained by Newton's theory. This residual effect is explained by Einstein's theory, the predictions of which differ slightly from Newton's in the strong gravitational field near the sun," end quote. So he's completely confused prediction with explanation. He's saying that, well, most of Mercury's orbit is explained by Newton's theory. The residual left over is explained by Einstein's theory. But the explanation in Newton's theory is a force, the existence of a force. So he's saying, well, almost all of it is explained by this force of gravity. It's just the residual that we use the curvature of space-time for, which isn't a force. What is he talking about? How can you both explain the same thing by recourse to force and not a force simultaneously? It's a strict contradiction. It doesn't work at all. Prediction, okay, even then it's a bit dodgy. We can predict the entirety of of Mercury's orbit, the entirety of it, by recourse to general relativity. We never have to bring in Newton's law at all. We don't, in fact. No astrophysicist worth their salt is going to try and predict where Mercury is going to be. In fact, any other planet. precisely speaking, you're not going to use Newton's theory, not in this day and age. If you want highly precise predictions of where those things are going to be, you're going to use general relativity. You're going to use a computer, but program with general relativity to get the position exactly right. So no, Mercury's orbit is entirely explained by Einstein's theory, entirely. Otherwise, it would be like saying, well, much of the life on Earth can be explained by creationism or spontaneous generation. Some of the rest by Lamarckism, and then a little bit left over is evolution by natural selection. I mean, how do we explain how GPS works? Most of it being explained by Newton's theory and the rest being explained by general relativity? I mean, Google Maps will tell you you're right outside the post office when in fact you're standing in the middle of a field if we use Newtonian gravity for it, but hey. Or how about gravitational waves? It is not that Newton's gravity is true in some domain or not. It's true or not. Surely the objectivists can agree with that. I know they talk about contextual knowledge, but contextual truth, that's relativist if anything is. The fact is, Newton's theory is not true. It works in some places because it's an approximation containing some truth, but strictly false. It's an approximation to reality, not reality. Approximations to reality are not reality. They are not the truth. And even where it works, Newton's theory, it never works exactly. Newton's theory, the predictions looked at high enough resolution do not correspond exactly to where any of the planets are. Mercury is just a spectacular case in point. So there we have it. Most of Mercury's orbit is explained by Newton, and just the remainder, just the correction, is explained by Einstein. So what this means, taken literally, is most of Mercury's orbit is explained by an inverse square law for force. It's explained by a force, and the remainder is explained not by an inverse square law, but by a metric and tensors and the curvature of space-time. So how does reality know what to invoke and when? How does it know that, well, for now gravity is a force and now for the remainder it's the curvature of space-time? No, it's all wrong. It's all the curvature of space-time. That's what gravity is. That's how we explain, not merely predict, explain what's going on. Not merely with the precession of Mercury's orbit, which is the example being used here, but all orbits, all falling objects, all tides. Every single gravitational effect is a manifestation of the curvature of space-time. It has nothing to do with a force. It has nothing to do with an inverse square law. That has been refuted. The inverse square law is a nice heuristic. It's an approximation to reality in some way, shape or form, but known to be false. And yes, in Popper's conception, sure, Einstein's general relativity is an approximation to reality as well. We don't know how it's false. We expect it to turn out false. We can't say it will turn out false, as incorrectly implied in this text, because we don't know for sure anything, including that we're going to find the successor. We hope to. We're trying hard to. We expect there must be because, the theory of gravity, general relativity, just doesn't comport properly with quantum theory. All that's missed. All this context, all the richness of the history of science, and the philosophy of science, science itself, and actual physics, it's all missed here. This is a fictitious story about how science works. So it makes no contact with what's really going on. Science is not merely about predictions. The orbit of Mercury is not explained, not just predicted, explained by Newton. It's explained best, explained only, so far as we know, by Einstein's general relativity, by the curvature of space-time. And whatever the successor is, we don't expect it to go back to being forces. Anyway, the author goes on. Einstein did not refute the laws of Newton, just as Newton did not refute the laws of Kepler. In both cases, the truth of the earlier theory was presupposed, and then a more general theory was developed that applied within an expanded context of knowledge. And in both cases, the expanded context of knowledge included small discrepancies between new data and the old theory, which were then explained by the new theory. This is often how science progresses. End quote. That is completely false. Einstein did not assume Newton true and take him further, as was just claimed there. The truth of the earlier theory was not presupposed. The truth of the earlier theory was, I say again, that there was a force. There was this force, this pull, this attraction. And in fact, it moved instantaneously through space, which is a problem. That was only solved shown to be unnecessary, false by the existence of a new explanation, doing away with the need for forces and instantaneous action at a distance. Einstein did not assume Newton true. He, from the ground up, changed the foundations of what gravity, time and space were. The poverty of the analysis in this book is absolutely striking. It's a very desperate attempt by someone who knows something about the history of physics to salvage induction. They are dogmatically wedded to objectivist epistemology. They need, for whatever reason, to salvage it from, well, I guess to some extent, the influence of Popper or wider understandings of the history of science. They need to try and salvage it, but they can only do so by literally butchering the history and the science. It's true desperation. But the author goes on, quote, "There is only one aspect of Newton's theory that was rejected rather than absorbed into Einstein's theory. And in this case, one can only wish that Einstein had been consistent in his rejection. Newton treated the concepts space and time as existence, independent of bodies rather than as relationships among bodies. Thus, he viewed space as an infinite cosmic backdrop that exists independent of the bodies placed in it. And he claimed that this backdrop has real physical effects on the bodies that accelerate with respect to it. Newton offered scientific arguments to support his view of space and time, but these arguments are non sequiturs. Absolute space and time played no role in the reasoning that proved his theory. Thus, I had no need to mention these ideas while presenting his discovery process. In fact, absolute space and time were intimately connected to Newton's religious views, and therefore they are an arbitrary element in his theory." End quote. So here we're just saying, well, Newton was religious, and so this is why he had this vision of space and time. But again, that is not, he begins there by saying there is only one aspect of Newton's theory that was rejected rather than absorbed in Einstein's theory. And he's talking about space and time. No, he's not. No. Force. About the gravitational force. The force of gravitation. That does not feature in Einstein's theory. It is clear. There is no force. There is no action at a distance. There are many aspects of Newton's theory that don't appear in Einstein's. It is laughable. There's no mention of Eddington's experiment. Okay, the idea that starlight bends more during a solar eclipse than it does under Newton's theory, falsifying, refuting Newton's theory. That's an egregious omission, and one might presume deliberate. We can only understand why Newton's theory is strictly wrong by recourse to experiments like that or any of the other countless observations as of this date, such as Mercury's orbit, where it makes the wrong prediction. It is wrong, period, full stop. It's not just about the wrong prediction. It invokes, mind you, things in reality that don't exist, period, full stop. It's wrong. There's no mention of how the force of gravity under Newton's theory moved instantaneously between bodies. And that was replaced by an influence from gravity, the curvature of space-time, that was limited by the speed of light. There's no concern here about the relativity of space and time, rather than being a fixed space and time of Newton. This is an absolute crucial difference. He tries to get there, but he says it's to do with religion or something. Okay, so enough of that. There's just not enough time to do that kind of thing, as you can see. Read all the books with all the egregious errors in history and science and misinterpretations of Popper, and can't read more on induction. There's just such a poverty of epistemology there. It's root and branch false. So this is me doing my best. So let me go back to Thomas, picking straight up from where I left off last episode. Thomas goes on. He writes, quote, "Once one has a series of first-level concepts that are generally identified by referencing that which can be observed in reality, the referent and the meaning of the concept, one can then use these concepts together to make sentences such as the above definition of a cat." Then he writes some more I'm going to skip over. He says the same sort of thing happens with bird, snake, running, which is an abstraction from the conceptualized animals that can run. Technically speaking, the above definition of cat is formed from both first-level concepts and higher-level concepts, and would not be the definition given by a young child who may not yet have the concepts of animal or communication. Just pausing there. You don't need to have the concept of animal or communication before you have the concept of a cat. That's just a misconception. Again, people have problem situations. The child might have no clue what an animal is and might learn what a cat is first, because there might be a cat in the house and no other animals. Might be one of the first things they learn is the word cat. And only later they realise that there are these other things out there. And much later than that, that all of these things fall under the umbrella of animal. You don't need animal first to form the concept of cat. This is all cart before horse. This is all a complete misunderstanding of how knowledge creation works and therefore how learning works. Thomas kind of admits this. He goes on to say, at the early stages of concept formation or using concepts and defining them, a young child with a small vocabulary will point to the household cat and say cat, which is an ostensive definition in this context. End quote. Which would, in the mind of the child, mean that that thing's a cat. That thing's a cat. Are dogs cats? Now, how can they rule out that a dog's and a cat? What do they understand? You don't know what they understand cat to mean at that point. They might not either. They just think it labels this one thing that lives in their house. But the problem with this way of talking about philosophy at all, full stop, epistemology, full stop, is he's imagining something in his head about this cat. This kind of philosophy is just so divorced from reality. It's not real philosophy. I don't regard this as real philosophy or epistemology at all, because it's not connected to problems. It's one of those situations where people just go, imagine this situation, like a trolley problem. Imagine this situation. Imagine you're at home with this child, and the child points at something and there's a cat. You need to bring it back to what actually happened in history, or what actually is going on right now in the history of ideas, how knowledge is created. This is not about how biological knowledge is constructed. It's not about science. It's not about concept formation, despite the fact he's calling it that. In fact, it's about how children learn language and about how people define words. And insofar as it is narrowly focused on how to define this word cat, well, it doesn't even get that right. Cats and snakes and so on are biological organisms. Knowledge of cats comes to us, in truth, via biology. Even when explaining to a child, when they have learned this word cat by a process of guessing and then checking in the way I've described earlier, eventually there comes a day when they learn that thing on television or at the zoo is called a lion, and that's a cat too. And that can be shocking to them because it looks nothing like, well, it looks something like, but it doesn't exactly look like the cat they've got at home or the other cats they've seen. So they begin learning about big cats. And then they learn, there's this whole class of organisms that are actually characterized by explanations coming from biology. These things are carnivorous, kind of like dogs, but instead, most of them have got retractable claws, unlike dogs, although not all of them. Cheetah doesn't have a retractable claw. But these cats, they're apex predators, and you only find them in some places across the world, except domestic cats, which are actually some kind of exception to the rule, exception to everything else that we know about cats, because they don't usually look at something like a human being as being a food source. And if the child pursues this line of questioning, which is what happens, they just keep coming up with more questions, in other words, more problems, and if they pursue it long enough, then they get to a deep understanding from explanatory science. They will learn about evolution and genetics. Those are the real explanations of cats. That's the real knowledge of cats. And how that knowledge is formed is not even plausibly, not even the slightest, to do with how a cat is supposedly this or that thing that jumps and meows and runs and so on. Evolution by natural selection is genuine knowledge, as is knowledge of cats. But Darwin did not observe evolution by natural selection. It occurs over timescales of thousands and millions of years. No one sees species evolve. Maybe bacteria through a microscope, but not really. Darwin formed the concept, if you like, of evolution by natural selection by guessing and then making predictions and checking. It was a whole grand explanation of reality, not observed in reality, but merely checked for consistency against it. Did it solve the problems? Did it answer the questions about why there are all these different species? Knowledge, the real stuff, is simply not about definitions. It's not about what a cat is defined as being in the main. It's about why some animals count as cats or not, why this class of animals, Panthera, live in the places they do and what they do, their evolutionary history and unique genetics. We must, if we're doing epistemology, grapple with all this. Philosophy, and in particular epistemology, is not about the definition of words. But this is what Thomas is implying. This is what objectivism kind of hedges towards. Thomas goes on to say, quote, So one makes observations, mentally abstracts out the similarities. Well, I have to sort of pause there, end quote. You make observation, you mentally abstract out observed similarities. The question is, how does it work? How do you mentally abstract out these similarities from your observations? How does that work? What is the role of observation? Again, let's take it back to actual reality for a moment. Prior to the 1900s, it was well known that Newtonian gravity explained almost everything moving under the influence of gravity. Apples fell, rocks rolled down hills, tides went in and out, and planets moved across the sky. Newtonian gravity seemed perfect. It was knowledge. Now, Newton did not look up and see his inverse square law of gravitation. Were knowledge creation that simple, we would not have needed to have waited until the 1600s when Newton wrote his Principia to tell us. He didn't have just huge tables of data gathered about all those things, like tides going in and out, and then extracted from that the inverse square law. People would have observed the real world and induced knowledge if they could just look, record some observations, and then write down the inverse square law. But here's a deeper problem. Prior to the 1900s, for some decades, it was known that while the theory, Newton's theory, seemed perfect, and thus it earned the title of the law of gravity, Mercury just would not obey. It was a rebel. Each time the law was applied, Mercury simply appeared in a place where it should not be according to Newton's law of gravity. Astronomers postulated hidden planets gravitationally perturbing Mercury's orbit. They suggested Vulcan, a mysterious planet on the other side of the Sun to Earth, on its orbit but behind the Sun, so beyond us at that time to observe. But that theory failed. Decades went by, no solution. It took Einstein to solve it, but not by observing Mercury over and over again. The solution to Mercury's usual orbital characteristics did not come from observing Mercury night after night and generalizing or inducing. It came from Einstein, in the first instance, looking into mirrors and wondering about light reflecting from that mirror. It came from Einstein considering magnetism and electricity and their relationship, and how when negatively charged objects in a magnetic field repelled each other, that when they were made to move, that force was different, and yet there shouldn't be, because whether the charges are moving or not depends on one's frame of reference. Einstein was interested in time and space and light, and he was creative. And after decades of considering all of those things, basically sitting at a desk and thinking, he developed special relativity, which had nothing to do with Mercury. But without it, without special relativity, he'd never have gotten general relativity, and then without that, no solution to Mercury's orbit. The knowledge of why Mercury's orbit does what it does did not come from ever more observations being generalized into some law, or induced from observations or anything like that. It wasn't extracted out of a table of data of Mercury's positions around the sun over time. It came from problems arising elsewhere and in the mind of a physicist working on light and magnetism and time and space. And then and only then was the solution to Mercury's orbit revealed, a manifestation of the curvature of space-time. But we don't see that either. Space-time, it's known to exist, and also not known to be observable in the usual sense of the word. We can't see it. We can see its effects. Prior to this, space was just another word for nothing. It was another word for emptiness, for what's between the actual stuff that exists. But now we know space is a complex fabric that can buck and weave. Indeed, so is time. Indeed, time and space are both manifestations of the same more fundamental entity, space-time. We know it exists. It is crucial in how global positioning systems work and why gravitational wave detectors are a thing, why neutron stars and black holes exist. And black holes, there's another thing we can never see directly or observe, only the effects. But we explain their existence because we cannot observe them directly. They appear in our best explanations, not because we observe them, but because the explanations we create say they do. Then Thomas goes on to write another paragraph. I'll give you a sense of what he writes here. The observed existence as a unit to compare other similar existents omits the measurements and unites the units in order to make the abstraction a specific mental entity, the concept. And this concept is open-ended in the sense that the same concept would apply to any future observations of other things that are similar to the first observed things that were conceptualized, such that those newly observed similar existents can be mentally incorporated into the previously formed concept. And so he goes. Again, my problem here is that this is abstract philosophy. It does not begin in how does science or history work to create knowledge. It is just focused on how words are defined or how we learn a language. There's this ethereal thing of concept formation. But it gets all that wrong anyway. We want to focus on epistemology. So let's skip down to something where he almost gets to this. Quote from Thomas. As it turns out, there are also first-level inductive generalizations that work similar to first-level concepts, in that one can simply point to those aspects of reality and then state the causative generalization, i.e., flipping the light switch turns on the lights, or pushing the ball gets it to roll, or typing on a keyboard displays alphanumeric characters on a computer screen. A first-level generalization is one in which the causal sequence or relationship is given in observation. In other words, for those causal events observed, causality is given in observation and requires a minimal effort to extract out the relationship. End quote. Well, which is it? Is it requires minimal effort, or is it you observe the causality? It can't be both. If you're observing the causality, if it's there, that takes no effort, doesn't it? He's saying minimal effort. Now, I would say causation is not at all obvious. Not at all obvious. Causality is a complex emergent phenomena. The laws of dynamical... In fact, put it this way. The dynamical laws of physics are time symmetric. This means that although we observe the past causing events in the future, it's also equivalent to say the future causes events in the past. What am I talking about? Well, as a matter of physics, look, a kettle is boiling. Why is the water turning into steam? Well, it's because the heat source determines that the bonds between water molecules will be broken and they turn into a gas. But what determines that the heat source is there? Well, equivalently, you can say, the heat source must have been there because the water turned into steam. Only possible if the molecules of H2O that the water was made of were broken at some point in the past. And they were broken in the past because the heat source was determined to be there. Determined why? Because the bonds of the H2O were broken. So the future has determined the past, determined the existence of the heat source in the past, given some future state. The future determines the past as the past determines the future. This is physics according to deterministic laws, because the laws are time symmetric. But if you ignore physics and you ignore science, you get this stuff about causation all messed up. The concept of causation is emergent because some things are possible in the universe and some things are impossible in the universe. But not all possible things happen in our universe. Why? Because something must cause stuff to happen. So cause actually comes after considering what's even possible. What is possible, given the laws of physics, is logically prior to what happens, which is to say, what is caused to happen. If you want to do fundamental science, epistemology, and philosophy, one needs to appreciate this kind of thing, or else disconnecting physics from philosophy means you, again, abstracting philosophy into the realm of reason disconnected from reality. Reason is powerful, but it needs to be constrained by reality. We can reason our way to all sorts of fallacious misconceptions. For example, Euclid's elements were reasoned into existence. They make claims like, given 2 points on a sheet of paper, a single unique line can be drawn through it. Just try it. It is mathematically obvious. It is perfectly reasonable. Try it yourself. Draw any 2 points on a sheet of paper. Now, draw a straight line through them. How many straight lines can you draw through them? That's reason. There's your observation. You've learned something that Euclid did and his followers did, that through any 2 points, only one unique straight line can be drawn. Nevertheless, it's false. And this is simple logic. Simple logic that I'm about to show is false. Basic mathematics and geometry. It's mistaken. All you need to do is to fold the piece of paper and recognize now how many multiple straight lines can be drawn through it. One needs to Think in more dimensions than just two. You could punch a hole straight through one of the holes you drew and out the other side with a pencil, the pencil itself now serving as the straight line. And you might say, oh, that's cheating. No, that's not what you meant. No, it's what I meant. It is what I meant. The point is that even with my clear instructions, you misinterpreted things. I spoke clearly and reasonably in the way the issue is put in almost every place. It's false. There's no point now stamping your feet and saying, unfair, I was tricked. No, you're fallible. Communication is fallible. Observation, including observation of my words, is fallible. And knowledge is not obvious, not easy to come by. It needs to be guessed, and error is everywhere. But you've learned something now, hopefully, and you know better. Popper can account for this. Rand and objectivism cannot. Okay, Thomas goes on to say, quote, this is a form of induction as presented by Peikov and Harriman in their works on induction, and it is important to point out that the statement must be a statement of a causal relationship and not just a generalised observation that is not connected to causation, i.e. all swans are white is not a proper or valid causative generalisation. And so it is not an inductive statement according to Peikov and Harriman because it is only speaking in terms of identified causes that one can be assured that the conceptualized abstract inductive generalization will apply to all members of that causative class. All swans are white is only an identification of the swans one has observed in the past, but since it is not causative in nature, one has no assurance that any future swans will be white. In fact, historically, they were all thought to be white until some black swans were found in other parts of the world. In other words, it is by identifying causes that one comes to understand the world abstractly in terms of scientific principles, when other types of historically considered inductive statements would not discover what the cause of the effect is and would not provide any guidance as to whether to be able to expect more of the same relationship identified or not. End quote. Well, to me, that is just an extremely torturous way of saying induction is false. We need a better way. And yet the cat example above that was used simply represents the all swans are white example. It just adds that cats have claws and feet and so on, and well, you keep on adding things to that. There is no substantive difference between the swans example and the cat's example. You need an explanation. You can consider my example of boiling water, www.bretthall.org/blog/induction. In short, what that is you take a beaker of water, you put it over a constant heat source like a stove, you stick a thermometer in it, and then you take your data, you graph the temperature over time. After 1 minute, the thing is 30 degrees Celsius. After 2 minutes, it's 40. 3 minutes, it's 50, and so on, you keep on going. After a certain number of minutes, you get to 90 degrees Celsius, and then you ask people to make a prediction. Induction would have it that you make a generalization, right? Now, on what basis do you make this generalization? Well, unless you already have a theory, but where did you get the theory from? Not observation, obviously. But unless you have a theory, you can't make a generalization. Induction would have it that you draw a straight line because it's going up consistently, and it does. It goes up in very close to a perfectly straight line trend. Every minute you're getting another 10 degrees rise. So shouldn't it go from 90 to 100, and then from 100 to 110, and from 110 to 120? That's what induction would say, inferring that the past resembles the future, inferring that you can derive from observations a concept. You can generalize. You can scientifically induce. But it's completely false. It's not what happens. And you do a test and you find out, well, actually at 100 degrees Celsius, the temperature ceases to rise. The thing boils, the water boils. And at its boiling point, temperature doesn't rise, even though it's still being heated. So what's going on? Well, you actually need a substantive scientific explanation involving things like latent heat and specific heat capacity and temperature and all sorts of stuff. And none of those come from observation. They're guessed. And you derive from that your predictions. But no amount of collecting data and drawing lines is going to get you there. No pair of data of time and temperature allows you to extract out from that water the idea that, well, at 100, something surprising happens. Thomas goes on to say, at the stage of first-level causative inductive generalizations, usually the concepts already exist. One has formed them previously. End quote. But how? So when you begin this inductive process, usually you begin with concepts that already exist. Where did they come from? Not by induction, obviously, because you're explaining the inductive process. You're explaining the inductive process by recourse to concepts you already have formed. Now, Rand would say, and Rand wants to say things like, when you read Rand, she goes, well, you have to begin with axioms. You have to begin with the existence exists, which is vacuous. It's not a genuine axiom. But she thinks from that you can then begin mathematically proving everything else, which is completely false. It just doesn't work. It's beyond the scope of this right now. Thomas goes on. What he's claiming to do is, quote, one is simply relating concepts to other concepts in a causative manner without any further types of measurement omission involved, because the measurement were already omitted when one formed the original concepts, like switch, light, ball, rolling, typing, computer screen, were already formed following the process of concept formation stated above, end quote. But the process of concept formation was, above, let's recap what he was saying earlier. He said, quote, you notice the similarities of various things observed within a context or an abstraction from the background, which requires a type of selective mental focus. And you unite the various observations together by omitting measurements while retaining the differentiated concepts, namely the concept, i.e. the cat, and then define this concept either by being able to point to instances of those things which are subsumed under the concept or in terms of concepts already created, so as to start building a conceptual hierarchy, end quote. Okay, so putting aside that, for me, it's just almost impossible to pass because of the idiosyncratic use of jargon here. Measurements, differentiated characteristics. At no point do we get to know how the concept is arrived at. It's circular. Now, the questioner might ask the objectivist, what is concept formation? And the objectivist says, well, it involves this process called induction. And the questioner will say, well, what's induction? And the objectivist will say, it's a process of concept formation by generalizing things from observing particular instances into universal laws, into concepts. And the questioner will say, well, how does that work? And the objectivist will say, well, you observe a creature, for example, has claws and fur and so on, and you thereby learn that all of these things, these instances, are cats. And the questioner will go, but what about if you observe a furry, clawed creature with all those characteristics? It's not a cat, like a possum, something new. And the objectivist apparently says, oh, no. That's not induction. That sounds more like an all swans are white kind of thing, which isn't induction. That's not what I'm talking about. Concept formation is the kind of induction I'm talking about. Oh, the questioner says, well, what's concept formation? And the objectivist says, well, it involves induction, you see. And the questioner says, well, what's induction? You can see I'm in a circular argument at this point, which is exactly what this paper is. It's a circular argument. It says concept formation is induction. Right? Induction is not this process where you're just talking about all swans being white, given a certain number of instances of swans. It's not that. It's not as simple as that. Oh, okay, then what is it? Well, concept formation sort of involves looking at these particulars out in the world, and you take all these different particulars and you unite them together, you see, and you develop concepts from previous concepts you got. Where did you get those previous concepts? Oh, via this method of induction. This method of induction is where you go out and you look at these generalized features of the world, all of which have something in common, you see, and then you're able to form this concept, and this concept is a new piece of knowledge that you've got. But how did you form the concept? Well, from the generalized instances. But isn't that like induction, like the all swans are white thing? You're just saying all these things. Oh, no, that's not what I'm talking. I'm talking about concept formation. You're in a circle. You're in this frustrating circle where you're not learning what concept formation is. You're just being told that it's induction. And then when you're asked what induction is, you're being given the same story that everyone's always been given about induction, that it's about observing stuff repeatedly. He goes on, quote, Thomas says, from time to time, new concepts may have to be formed to fully conceptualize the inductive generalization, end quote. So close, almost correct he's got there. He's got it. He's saying new concepts have to be formed. He can forget the word fully. He can just say, new concepts have to be formed to conceptualize the inductive generalization. But in fact, you can forget the inductive bit there now too. So his sentence there where he said, quote, from time to time, new concepts may have to be formed to fully conceptualize the inductive generalization. Let's just change that. I'm going to get rid of the from time to time. I'm just going to say new concepts may have to be formed to conceptualize the generalization. And then, end quote, then we get closer to the truth. But conceptualize is a fancy word, so you can do without that. New concepts are formed, and this allows generalizations to be made. That's what we'd say under a Popperian framework. For example, the concepts of thermodynamics and latent heat and particle theory allow us to make a generalization like water tends to boil at 100 degrees Celsius at sea level under standard conditions. That's our general statement. Now, there are exceptions, and we can say why, but the generalization is not inductive, it's actually deductive. It's a logical consequence, a deduction from a much deeper theory about chemistry, thermodynamics, and the concepts of latent and specific heat. And Thomas goes on to say, so after saying, from time to time new concepts may have to be fully formed to conceptualize the generalization, such as when one observes that a changing electric current leads to a fluctuating magnet or compass placed near it. End quote. So that's good. We're seeing some kind of actual science, but it's very superficial and imprecise. Yeah, a changing current in a wire can cause a compass needle, or better, a freely moving magnet placed reasonably close to it, to move. This was Ørsted's experiment initially. This is because of a deeper law of physics that changing electric currents, or more precisely, moving electric charges, generate magnetic fields. More precisely, some sort of flux change anyway. These things generate magnetic fields. That's the explanation. The observed effect of moving compass needles is the explicandum, okay, what we need to understand. And it's also a test of the theory, or perhaps better regarded as a demonstration of the effect. But we don't see electromagnetism. We see moving compass needles. But why? Well, that took years to figure out. Indeed, many explanations have been purported and give partial accounts. Today, why magnetism exists at all in the first place comes down to relativistic effects. And we don't observe those. They are not induced. They were conjectured, and by Einstein initially. He goes on to say, quote, so concept formation can definitely be involved in identifying a given causal inductive generalization, but does not have to be involved if the concepts were already formed before making the new observations. End quote. Well, almost. We can do away with this whole shoehorning in of inductive generalization. There was no generalization involved in Ørsted's experiment. He never generalized to electromagnetism. Faraday proposed it, and he said of his own theories, I hold my theories there on the tips of my fingers so the merest breath of fact could blow them away. End quote. He understood, Faraday understood, he explained electromagnetism, and he understood that knowledge was conjectural. He got it. He knew he did not derive or induce generalizations from observations. He was guessing at the world, not guessing at true knowledge, but useful information about the world that solved problems. It was a great guess that mere fact could refute. Thomas goes on, quote, with a generalization, one can have something like, flipping the switch turns on the lights. This would be a first-level generalization of the type spoken about in Peikoff's course and in The Logical Leap, end quote. Well, the logical leap. The leap is a conjecture. It's a guess. It comes from within. It can't come from without. Nothing is leaping out there in the world. It's leaping within, this logical leap. Leaping from a problem to a solution, or a purported solution, a guess. And an observation may be a problem, or a mistake. Observations of faster-than-light neutrinos at the Large Hadron Collider would, according to an objectivist picture, mean we've observed that Einstein's wrong, as his theory was that nothing can move through space faster than light. Only Popper understands. It's all interpretation. It's all theory-laden. Observation's not that simple. You don't just observe the facts of reality. You don't observe neutrinos moving faster than light. You don't observe compass needles moving. You don't just observe trees. And in the case of the neutrinos, what was actually seen was an error. They only appeared to move faster than light because the equipment was faulty. We only appeared to observe something about reality. We didn't actually observe reality. Those scientists who apparently observed that thing retracted their paper. It was an error. It turned out nothing went faster than light. A mistake with cables or something. So too with the sky is blue. That's just a manner of talking. The sky appears to be blue. The sky appears to exist. There is no sky. It is not a substance. It is not a thing we can see. We are seeing sunlight scattered by molecules of air towards the ground, and the blue photons get scattered the most. We see that and say the sky is blue. Observation is theory-laden. We see a thing and we say, oh look, a tree, and then the guide at the Botanic Gardens tells us, sure, that looks like a tree, doesn't it? Appearances can be deceiving. Now, observation won't tell you, but that's actually a red flowering maple. And now, if you look at that, what you thought was a tree towering above you, and you've just heard, the Botanic Gardens guide say maple, and you know maple is a tree, and you're a pretty dogmatic, let's say, objectivists, and that's just a stupid gardener. But then they go on to explain the difference, botanically speaking, between shrubs and trees, but you tune out because you think, well, my senses have given me reliable knowledge, and you kind of refuse to admit you are wrong. You still go on thinking. But no, when I look at something and I see a tree, I know it's a tree. I know a tree when I see it, damn it. This is one of those edge cases I've heard about perhaps, but basically the idea is I see the facts of reality. I observe the facts of reality. If I'm looking at a tree, I know it's a tree because I can just see a tree. Who cares about shrubs? Well, this is the problem. This is the problem with objectivist ways of thinking. You might even do the same thing when it comes to epistemology. You might notice that there are severe errors with objectivist epistemology. You might hear about something better like Popperian epistemology, but you're going to treat it like a trip to the Botanic Gardens where the botanist who's guiding you is saying, it looks for all the world like a tree, but in fact, technically speaking, not a tree. It's a shrub. And you can stamp your feet all day, and you can say, no, this isn't one of those cases that completely refutes my epistemology. If my epistemology comes down to you see the facts of reality, you observe the facts of reality. If you're looking at a tree, then you're observing a tree, and that's the fact about reality. Not realizing you could be mistaken about something as simple as a tree, because not everything that looks like a tree is a tree. Some shrubs look like trees, and a shrub isn't a tree. And that is actually a refutation of your claim. You don't understand what a tree truly is. So I'm going to move a little bit more quickly and just pick up some things where I think, Thomas gets a few things almost right. He says at one point, inductive generalizations are open-ended in much the same way that concepts are open-ended. They relate to many different instances of conceptualized inductive generalization, end quote. So yeah, open-ended, that's good, that's right. It also means, again, that observation does not come first. It's open-ended, we can make infinite progress precisely because we begin with problems. If we don't have a problem, again, we're just going about like moving through the world and not worrying about how knowledge works. But then if you do see something that makes no sense, then you've got a problem. Now, it could be your idea. Your idea could be wrong about, say, what trees are, or what relativity says, or what is possible about speed. Or it might be you are wrong, that you even made the observation. You thought that was a tree, but you were wrong. You thought you saw particles going faster than light, but that was wrong. The theory might be wrong, or your observation might be wrong, or both might be wrong because you're fallible. The point is, knowledge cannot be gotten from mere observations here. That gets you nowhere. You need to conjecture. And it's not inducing. Inducing from what? Not observations. Other knowledge? No. Because no existing theory might work. It didn't for Einstein. It needed to be literally created. How's that done? Well, we don't know exactly. If we did know, we could write an algorithm for it and then program it like a recipe into a dumb computer so that those dumb computers could be smart computers. And then they could do this knowledge creation stuff. All we know is that we do create knowledge, so we must when we encounter a problem. One day we'll know how, just not yet. When we do, we'll program computers to be just like us, who can also explain stuff, generate explanatory knowledge. And Thomas goes on. He says, quote, "But notice that just as one has a unit that serves as a standard in concept formation, i.e. any given dog can be used as a standard for the concept of dog, one can keep the whole causal sequence in mind of turning on lights, such that any given means of turning on light can be used as a unit that serves as a standard to make further integrated observations, such that when one comes across some unique way of switching on lights, one doesn't have to start from scratch and reconceptualize the causal sequence," end quote. Well, okay, but where did the causal sequence come from in the first place, or knowledge of the causal sequence come from in the first place? This is all too simplistic, too abstract, too disconnected from actual big ideas and proper explanations and the history of science and problems in science and anywhere else. It's just not a big problem how the term dog is defined or how lights are switched on. The concept or explanation of what a dog is, for example, is not the same kind of thing as what the dictionary definition of what a dog is. The real knowledge from which the definition is derived involves grand theories of biology, canines and speciation, and that goes to evolution and even genetics in the end. If a child quite reasonably asks you, as they often do, spend some time with a young child, but why, but why, but why, each time you give them a deeper understanding of some question, then beginning with dog, what is a dog, you'll eventually get to evolution. You won't go through the scheme or anything like it that Thomas is talking about here. Again, talk to a kid sometime. Really understand what's going on. They don't want a simple definition. They don't want to be told when they're asked, what's that? That's a dog. What's a dog? A dog has fur and barks and has 4 legs. And look, those are the dogs. And look, here are examples of dogs. No, they will have more questions. They might see a 3-legged dog. They might want to know why wolves and hyenas are not dogs and more besides. Either they'll get bored, their questions will continue to be answered until such time as they no longer have any problems, they have none left, they've exhausted all their questions. Or if you're any good, you will keep on answering, and you will indeed end up with a lack of answers yourself, or you'll end up in evolutionary biology. And you may eventually get to a point where you say, that's all I know, or in fact, that's all anyone knows for now. And you can say, people never stop learning stuff, but this is all I've learned so far. Maybe we can learn more by doing some research ourselves together. Let's go on the internet. Or maybe you can learn how this evolution stuff really works better, because I don't understand. It's kind of our job as people to keep on learning more and more and solving all these kinds of problems about what dogs are and stuff. It's a lot of fun, isn't it? Lucky that we can do it, because the poor old dog over there, it doesn't even know what it is and it can't learn anything, so we have to learn. And the child might even ask, why can't they learn? Why can't a dog learn this? And then you'll say, aha, well now you're asking about what people are. And you're asking about something called knowledge and epistemology. But at that point, you're asking about how we know stuff. And hopefully you won't go into mentioning fancy words like maybe epistemology. And certainly you won't go into mentioning jargonistic words like inductive generalization or induction at all. Stick with guesses. Not just because all kids understand what a guess is, but because it's also actually true when it comes to how knowledge is generated. Let's guess. Let's guess what a dog is. Can a dog have 2 legs? Oh, usually not. Does a dog like to eat plants? Well, usually not. Can a dog talk? Well, usually not, and here's why. And then you use the word check. Let's check that. Let's do a little test outside. This is called an experiment. Let's check on the internet. Maybe someone else has checked before. We can check what they said. Guesses and checks. Guess and check. That's how it works. That's how it all works. Thomas goes on. Then I won't read all of this. He says things such as, I'm expanding on the idea of a unit that serves as a standard and applying this to generalization, scientific induction, and philosophical induction, each of which deals with a particular causal sequence of specific types. Instead of just retaining one item at a time like one does with concept formation and having one thing as the unit that serves as a standard, the entirety of a causal sequence can be retained and can be used as a unit that serves as a standard for any further understanding of similar causal sequences. And he goes on. And he's just repeating the stuff about generalizations and causal sequences and concepts. And it's not explanatory. It's list after list and statement after statement of jargon. It's repetitious. It's not adding anything. There are no examples here, importantly, to talk about. Nothing from real life, no instances put forth, nothing from science or the history of ideas, where it has worked or where it could work. We need to be concrete in philosophy. We need to not be abstract. Sometimes it's unavoidable to be abstract, but only after we've dealt with the concretes, dealt with the actual problems that are out there. He goes on to say, let's just pick up, because pick up a bit where he actually mentions something to do with science. He says, in the case of electromagnetism, the scientific principles or inductive generalizations were well known for electricity and others for magnetism. But with a bit more observations, it was found that they could integrate these two into a broader generalization that a changing electric field leads to a magnetic field, and conversely, a changing magnetic field leads to an electric field, end quote. It wasn't just observations. Again, you're not just observing this stuff and going, oh, well, now I conclude electromagnetism and the laws of electromagnetism. That is far from the truth. You're not getting the laws of electromagnetism. This is the key thing. Yeah, sure, you can do Orsted's experiment. Put an electric current suddenly through a bit of wire and, yeah, it's going to move a magnet around. From that, it doesn't matter how many times you do that, you're not going to get the laws of electromagnetism. Nothing about that's going to give you Faraday's law of induction. It's not going to give you Ampere's law, Lenz's law, the Lorentz force law. Nothing like that. Nothing. You have to have a problem and then start properly measuring stuff and then conjecturing these ideas. He says, quote, one makes observations, mentally isolates out the observations, forms an abstraction, end quote. Makes observations and forms an abstraction. Mentally isolates out from the observations, this abstraction. How? Why is one observing the flicking of switches, by the way? Who has ever learned this way? Again, here's what actually happens in a household. The light goes on. The child thinks very early on in life, perhaps when they're still an infant, perhaps when they're still a baby. How did they happen? They're surprised. They haven't got words at this point, presumably, but they're surprised and they wonder, well, the light just went on. That's interesting. They guess it's when mum walks in the room because those two things appear to happen together. The light goes on, mum appears. The light just appears. Maybe they just think mum's doing it. Mum's doing it, but how? But then they notice they hear mum first and she always goes to one place in the room. Then the light goes on. Then maybe once or twice more they hear a click as the light goes on. Aha, there she is. Finally, next time, they get it more or less. There she is. There's that thing on the wall. All the guesses come together. The light goes on, has something to do with this thing over there on the wall that she touches. Then at some point much later on, they learn the language. They learn this word switch. There is none of this stuff, observe the switch over and over again. No, it's a problem people have, including babies. We learn a lot inexplicitly without being able to put it into words. My guess is, as infants who cannot speak, they know stuff like this. They know how light switches work and heaps more besides. They can't articulate it. So often they cry when they want something. It's also, it's all they have. All they have to communicate is to cry, and except for baby talk. I personally have a strange memory of being a very young child, maybe only about 4 years old myself. I could barely speak, I suppose. And my youngest brother, I could only just speak with, small vocabulary myself. And my youngest brother was still a pre-verbal baby. But I remember, even now, today, I remember completely understanding him then, his baby talk, his gurgling or his babbling. It wasn't English, but it was some kind of communication, some baby language. How did I understand him? I don't know how now. I've forgotten. I just remember. I remember I could translate what he was saying as if, at the time, I had not forgotten the inarticulate baby talk. I was in that transition phase between baby talk and knowing how to talk as a grown person. It's strange for me to think back now, but is the reason I simply know babies know a lot of stuff. They can ask for stuff and eventually they can ask for stuff in English, but they can actually ask before that too, long before they can talk. They have needs and wants and they want to communicate, they can't quite. They can try, and so you have to look carefully at a baby at how it's trying to get the message across. And they learn not by observation, but by having a problem, guessing a solution, and only then by observing, which is the check they do against their guesses already made. Knowledge comes from within, checked from without, and then it exists out there solving problems as theories in books and objects and things like bridges and rockets. Okay, this has gone on for a long time, so I'm just skipping a lot of other parts of this. Then I'm going to go to just specifically the areas where he tries to talk science. So he says, quote, to get the relationship that force is equal to mass times acceleration, F equals ma, one would have to measure the force exerted on the object, the mass of the object, and the acceleration of the object for each instance of one's observations, end quote. So this is completely false. I mean, more than anything else, we can refute objectivism. If this is what objectivist epistemology is, this is it. This is the cut and dried example of how it's just simply false. No one does that. No one ever has done that. A better way of expressing F equals ma, by the way, is to regard a, the acceleration, as a change in velocity. We may ask, why is the velocity of some mass changing? But then we have mass times the change in velocity. But mass times a velocity is momentum. So now we have a new question. Why does the momentum of something change? Well, the answer is because a force is applied. How does the force on something change the momentum exactly? Well, the second law tells us that the momentum of an object changes in proportion to the force applied. The problem with F equals ma is that it assumes m and a are constants, but they aren't, except in simple junior high school examples. There are situations, like rockets, where the fuel has mass. So the mass changes as the fuel's consumed. So what happens is there that the velocity increases at an increasing rate. F might be constant in that case because the thrust of the rocket is, but both m and v are changing, so therefore a changes as well, the acceleration. All of this is an explanation of why F equals ma in terms of more simple concepts like velocity, which is itself explained in terms of position and time. And m, mass, what is mass? Well, this is what science is. A series of questions and problems and solutions, explanations. The laws of physics, of which F equals ma is one very poor representation of Newton's second law of motion, are explanations of reality. We don't observe couplings of masses and accelerations out there in the world and infer forces or Fs. Indeed, if we tried doing that, we'd never strictly get F equals ma at all, because friction exists in our world, imperfection exists in our world. Newtonian mechanics has F equals ma as a conclusion, a theorem following from deeper assumptions. That's how it's arrived at. But again, you need to know physics properly, and you need to understand the history of physics to fully account for this. What problem was Newton solving? Even in the physics classroom, we're not looking at couplings of F, M, and A to induce F equals ma. Often what's done is we're looking at pulleys and pendulums and realising F equals ma is required as part of the explanation. But Thomas goes on, and he actually provides, you'd need to have F1, M1, A1, F2, M2, A2, F3, M3, A3, each with their own measurements, and then you'd conclude at the end of that F equals ma, which again is just the all swans are white thing. I'm observing this swan, this swan, this swan, this swan, they're all white swans, therefore all swans are white. What he's saying there is I'm observing F1, F2, F3. I'm observing F equals ma, F equals ma, F equals ma, F equals ma, and therefore I'm observing F equals ma. Okay, I'm observing this instance of F equals ma. In other words, what he's saying is you're told F is 8, M is 2, and A is 4. Okay, there's one trio. And then you're told F equals 10, while M is 2 and A is 5. Or F is 20, while M is 5 and A is 4. Now guess the relationship. Well, you've just been told, 3 instances of where F equals ma. So, of course, you're going to conclude F equals ma. All swans are white again. All swans are white again. It's so terribly wide of the mark. So terribly wide of the mark. What observations of that sort gave us general relativity? The laws of gravity, the actual laws. No one was collecting numbers and deriving the field equations of general relativity. After all, what numbers would that have been? How would you guess those relationships? Anyone can guess F equals ma given 3 numbers, but that's just algebra. It's not science. Science is messy. Only a non-scientist would ever come up with an idea like that about how F equals ma was arrived at. But you just do the actual experiment, by the way. Do the experiment in a high school physics lab. It's really hard, really hard. You barely get pairs that match that at all. There's so much friction all the time. You need computers at best and motion detectors and all sorts of stuff. And you have more complicated equations with pulleys and trolleys and a more complex version of the law, F equals ma, by the way, which only falls out at the end as a conclusion after much explanation and manipulation. If it was as obvious as Thomas is assuming here, why did we have to wait for Newton? Why didn't the Babylonians and the Egyptians and why didn't cave people have F equals ma? Or any other scientists for that matter? Because we can't observe the facts of reality. We can't observe F equals ma out there. But he carries on in the same vein for more of this, and I'm just going to skip over all of that. And he gets to, this is coming to his conclusion, he says again, quote, Aristotle defined induction as the process of reasoning from the observation of concretes or individuals to a general, or universal conclusion. I've tried to show that there are definitely times where one has to put considerable thought into deciding if two or more observed things belong in the same concept or not, end quote. Or in other words, Aristotle's definition of induction, which is just induction, as understood throughout history, doesn't work. And Thomas has noticed that, but he tries to salvage the term nonetheless. In doing so, he's confused about the process of knowledge creation. Like, happily, Popper has done all the work. And so this is why objectivists would benefit from reading Popper, not just saying, well, Rand was right about everything. So what she must have meant about induction is this. We've got to save this because Rand used the word. Let's save induction. But it's a dead end. Thomas says, quote, I think I have shown that concept formation, generalization, scientific induction, and philosophical induction have all enough components that they are similar, that these can be integrated into one concept of induction, end quote. No, he hasn't accomplished this at all. Induction doesn't work. Even his attempt to show it in science is just saying that it's the same old thing of, various trios of F's and M's and A's can lead you to concluding F equals MA, just the same as observing white swan after white swan can lead you to the conclusion that all swans are white. This doesn't work. And by the way, science and philosophy are domains of knowledge and explanation. Not predictions of that sort, not just generalizations. They begin with problems, and the role of observation is to decide between competing knowledge claims. That's the point of it. That is, as far as I can tell, a comprehensive analysis of the objectivist view of induction, as filtered through a fan, and one might very well say a scholar, an expert in Ayn Rand's objectivism, specifically the objectivist epistemology, Thomas Miovas Jr. And so I think I've done as much justice as I can to the paper. I think this counts as a refutation of the foundational claims of inductivist epistemology. And I hope the objectivists read a little bit of Popper. Okay, it doesn't mean that you have to reject all of Rand. And even if Rand herself says words to the effect that everything else is built on the epistemology, on the ontology, on axioms like existence exists, something like that, it doesn't mean you have to follow her there. You can preserve the good stuff. You can keep the good stuff because it actually solves a problem. In the Popperian framework, something like, the virtue of selfishness, let's say, capitalism, the unknown ideal. These works and the content in these works solve problems utterly independent of what she says about epistemology. They don't need to be built on a foundation of epistemology. And that's another story. We don't believe in foundations because you don't need them. I don't believe in belief either. But until next time, bye-bye.